Okay, so I heard we are live. Welcome to our session FP. Welcome to our session FP12. In visualization applications and machine learning. We have 4 interesting papers here which are going to be presented. And my name is Timo Rupinski, and I'm sharing this session. So the topics we have is very diverse. It goes from reinforcement learning over animal behavior, cultural heritage, and bomb-playing games. So we have a quite fun mix of papers. And we start with the first paper. And this one is called DRL Vis, Understanding Decisions in Memory in Deep Reinforcement Learning. And this is work done by Theo Jonet, Romain Boulemont, and Christian Wolf. And Theo is going to present this paper. He's a second-year PhD student, and his main topics are Vis and AI, where he focuses on reinforcement learning techniques. So in general, I would like to ask you, if you have questions about the papers, please use the YouTube channel, or if you prefer, you can also use Discord, and type the questions even during the talk when they come to your mind. That makes it easier for us to select the questions and read them in the proper order after the talk for the Q&A. With that, no further ado, I would like to switch over to the talk and listen to Theo talking about his work on deep reinforcement learning.
Hello everyone, my name is Theo Jonet. I'm a PhD student from Lab, France, and this is a joint work with Romain Boulemont and Christian Wolf. I'm presenting DRLVis, a visual analytics tool to explore the memory of a deep reinforcement learning agent in automatic navigation. You can check it up online, the link is in the slide. Automatic navigation has a wide range of applications, from finding the shortest path between pair of points to exploring unknown environments, or answering questions such as where are my keys? This can contribute to applications such as travelerless cars and social robots, among others. To speed up the training process and prevent robots from damaging themselves as they learn, we often use simulators as proxy tasks. In our case, we rely on the Wisdom simulator to provide navigation tasks from the game Doom. In this kind of task, a robot we call agent is set in an environment with obstacles such as walls and items to collect. In order to be successful, the agent must collect 4 items in a specific order. At each step, the agent must decide on one of its available actions and do it. Such a decision is made by a controller, which uses the agent's field of view as input and outputs an action. We use deep reinforcement learning as a controller. It consists in 3 stages. The first one is perception, which uses an image as input and outputs features extracted with CNN layers. Then these features are used by a recurrent layer we refer to as memory. Finally, based on the memory, the controller attributes values to actions and picks the one with the highest value. We are interested in the memory. Our hypothesis is that such a memory contains information on the agent's decisions, and therefore analyzing it may help experts understand them. At each time step, we gather the memory as a vector. We call rows of these vectors elements, and the dark color indicates that this element is active, and thus that it conveys information. The accumulation of memory vectors forms a heat map, but the heat map by itself, without any context, is hard to analyze. Therefore, we designed DRLVis, a visual analytics tool which contextualizes the memory with additional views such as timelines, observations, saliency maps, Disney projection of the memory elements, and trajectories. The workflow in DRLVis usually goes as it follows. The user starts playing episodes in which the agent gathers items. Now, let's say we are interested in how the memory behaves when the agent sees a green armor. We can branch the memory to filter timestamps in which the agent has a green armor in his field of view. We can then reorder the memory elements based on how much they were active during this interval. We can now zoom in to only display the most active elements, which may convey information related to the green armor. Then we can use timelines as an overlay of the memory to see how the green bar aligns with activations of the memory. If activations of an element fits the bar, it may indicate that they are related. Now, let's say we are also interested by the red armor. We can use timelines to directly filter the memory to only display intervals during which the agent sees the green armor or the red armor. We can also stack them for an easier comparison. Here we can see that the third element is blue when the agent sees an armor and orange in between. Finally, other views can also be used to filter the memory. Such as trajectories or Disney projection. These results may suggest a correlation, but of course further analysis is required to confirm or deny such an hypothesis. We have shown this tool to 3 experts who shared insights such as how the agent only focuses on the item it must collect and ignores the others in silence maps. How the agent uses some memory elements as flag to encode items it has collected. How DLVs can be used to detect actions patterns such as here where the agent repeats the same action for a while in dead ends. And how the agent uses one element to encode 2 items, the armors. Experts also provided feedback on their usage of DLVs, which was taken into account in the prototype we share today. We also used DLVs on other deep reinforcement learning models and tasks, such as base match and item collection based on their color. You can see them in our online prototype. We are currently working on using DLVs on robots deployed in real life, hence without any ground truth. We are also working on implementing memory reduction systems directly in DLVs. That way, we can use DLVs to sample memory elements and force the agents to only use those elements. As this requires for the tool to directly interact with the model, this is currently not available in the online prototype. But this can be done using Python scripts in our GitHub. Here, this toy agent has 500 memory elements, and we can see that when we reduce it to only 10% of that, the agent has still a somewhat decent behavior. This can be interpreted as the agent not using the complete memory. and thus that the expert may need to reduce its size before running another training. To warm this up, we made DRLVs, a visual analytics tool to explore how the memory of a DRL agent changes as it explores its environment. Using this tool, experts gain insights on how this memory is used and worked on using different memory sites for their models. Thank you for your attention.
So I see there's a couple of questions showing up in the YouTube. So the first question is by Shiva Magaravan. He says awesome work, which I can second here. And his question is, I guess reordering the rows based on different metrics, for instance similarity, could reveal patterns in memory activation. Some control here. We just try before. Okay, he doesn't have sound on my side. On his side, sorry. Maybe the technician can help out here. Maybe the others in the Zoom chat, can you hear me? It's not my microphone, is it?
Yes, we can hear you.
Okay, great, thanks. Okay, so technician seems to be gone. Maybe we postpone the question till later, and we have to fix it. I'm sorry for this. So let's just the presentation, and this one is talk on the topic of visual abstraction of spatiotemporal networks in collective animal behavior. So we will see how we can actually make sense out of these behaviors by means of motion glyphs. So it's somehow related, as it's also about motion in some environment. But it's from a different perspective, of course, entirely. And the talk is given by Aaron Kekmek, and he's a second-year PhD student at University of Constance, where he works on dynamic graphs and visualization thereof. And he will now tell us about the glyph design for the animal behavior. So please let's enjoy this video together now.
Hello everyone, welcome to the presentation of motion glyphs, a visual design which allows to explore dense spatiotemporal networks in the field of collective animal behavior. Let me start by giving you some background information. Collective animal behavior is a fascinating phenomenon appearing in many forms in nature. Prominent examples are the collective movement of fish schools, insect swarms, or flocks of birds. There is ongoing research in the field of biology to explain the mechanisms by which such collective group patterns emerge in these natural systems. In this work, we present a visualization design study in the field of collective animal behavior. In an iterative process during the study, we designed multiple glyphs for the analysis of spatiotemporal networks. Generally, the behavior of collectives can be modeled as spatiotemporal networks to analyze the evolving emergent properties of groups. For example, the recent work of Rosenthal et al. Analyzes evolving interaction networks of fish schools. In these networks, the movers are mapped to nodes, and the sensory information of a mover is mapped to a weighted link. For the visual analysis of such data, we developed together with domain experts motion glyphs. The approach focuses on reducing the visual clutter by abstracting the spatiotemporal network to glyphs. Furthermore, our design enables to summarize and display spatiotemporal networks at multiple levels of granularity. which allows domain experts to explore local as well as global network properties over time. Motion glyphs was designed over the course of 5 months in close collaboration with 2 domain experts. We followed the design guidelines by Lloyd and Dykes for geovisualizations to make the design process interactive. The main goal of the collaboration was to create a visual design to support the identification of group patterns over time in a large set of moving entities. The analyzed data in the study is tracked movement data of real-world lab experiments, in which the domain experts try to discover similar behavior involving group structures and outliers. The visual analysis of extracted spatiotemporal networks from such lab experiments remains challenging due to the fixed spatial positioning, which results in node overlaps and edge crossings for dense areas of movement. The temporal dimension of the data poses a challenge to present the data in a readable, scalable, and expressive manner. For example, the visualization of fully connected networks is not feasible for large groups of movers. We conducted interviews with 2 postdocs in the targeted domain to understand the user requirements. During the interviews, we investigated how domain experts analyze their data, which tools they use, and what potential high-level problems have to be addressed to understand collective animal behavior. Together, we derived the following domain problems which have to be addressed. First, in the application domain, it is crucial to investigate the relations of one movers to all other movers, to understand how one individual animal influences the behavior of the whole group, and vice versa, how the group influences the behavior of one individual animal. Second, it is important to identify movers of similar behavior over time, for example by applying clustering methods. And the visualization of relationships in such groups can highlight the underlying sociocentric processes in collectives. From these problems we derived 4 user requirements. Visualizing the raw data is essential as it helps to interpret and understand the emergent properties of groups. To explore the evolving relationships between movers, the domain expert should be able to relate time, space, and attribute dimension. The user should be able to interactively aggregate the data into meaningful units, which is crucial to abstract and simplify large movement datasets. And the user should also be able to explore data from an egocentric to sociocentric perspective. In our work, we also compare a selection of current related approaches to the defined user requirements. Most related work approaches are either not suitable for the exploration of temporal dynamics of movers, or they do not support an accurate spatial representation of the movers. In contrast to these approaches, motion glyphs comes only at the cost of implicit edge representation and the loss of some spatial accuracy for the interactive exploration of group structures. For a detailed comparison of the related work, please refer to the paper. The developed motion glyphs prototype allows to visualize single and groups of movers as glyphs. The single glyph displays one mover and abstracts the weighted network links. The arrow depicts the movement direction, and the inner circle of the glyphs allows to display movement characteristics, such as the speed of an individual animal. The outer ring of the glyph is essentially a donut chart with segments that aim to summarize the median link weights to other movers that are positioned in a specific direction. For example, the node link diagram of 4 movers will be displayed as 4 glyphs with implicit link representation. The cluster glyph presents group structures. For this, we apply a spatiotemporal clustering with different input parameters which a domain expert can later explore. For the interpretation of the cluster, we also visualize the underlying group structure as an additional level of detail. We display in the inner circle the underlying spatiotemporal network of the group as an animated node link diagram. The background color of the inner circle displays also the average attribute of a group, for example, the average speed. The node link diagram in the center of the glyph is also colored and encodes attribute information, for example, the speed of an individual mover. The outer ring of the cluster glyph again displays all abstracted links to all other glyphs. The size of the cluster glyph is mapped to the number of movers in the group. For example, again, the cluster glyph of a group of 4 movers looks like this. During the iterative design study, we also created alternative designs for the glyphs. For example, a first alternative glyph was inspired by off-screen visualization techniques, which also included the abstracted distance information to the linked movers. We We also designed other glyphs, for example a detailed glyph in which the whole ego network of a node is displayed in the outer ring. The alternative designs allow to display the evolving ego networks of movers in more detail. However, identifying changes and comparing values in the relatively small and complex outer rings was too difficult. Motion glyphs was implemented as a web prototype. The prototype consists of a temporal navigation panel and a feature panel to modify the visual mappings and the displayed cluster granularity. The prototype allows to display the evolving data as an animated node link diagram and also using the designed glyphs. The visual mappings in the prototype can be modified. For example, we can change the segment width of the abstracted links. In this case, a real-world dataset of 5 stickleback fish are displayed. The single glyph reduces visual clutter by not displaying the links and allows to identify patterns, for instance burst patterns in which fish accelerate shortly to catch up with the fish school. Next we show how the cluster glyph can be used to identify structural and temporal patterns. In this video a real-world dataset of 151 golden china fish is shown. First, switching from the node link diagram to the glyph representation highlights the advantages of the implicit link representation. Next we use spatiotemporal clustering to explore group structures in the collective movement. The cluster glyph can be used to identify apparent influences of movers and smaller groups merging and shortly dismissing again. The cluster glyph highlights many temporal patterns such as splits and merges, which again allow to further analyze the influences among the movers. Experts can perform a detailed investigation by tracking the movers or groups over time and examining the links between them via a mouse over. We can also change the cluster parameters to reduce the number of overall displayed movers. This helps to identify movers with distinct behavior. For example, this fish who is not clustered in any of the two groups during the merge process. To evaluate the motion glyphs prototype, we conducted a pair analytic sessions with 5 domain experts. Overall, the participants' feedback was positive. They were able to identify several interesting patterns. All participants agreed that the abstraction and aggregation is helpful and necessary in large groups or dense areas of the network. The results of the evaluation can be summarized by a quote. In high-density formations, the glyphs are awesome. In low-density formations, the network is much more important. Using motion glyphs, the participants could easily spot outliers, larger groups, and transitions in groups, such as split and joins. Some participants went even deeper into the analysis and identified roles such as leaders and followers. The participants also suggested improvements, for example to interactively allow the adaptation of the scaling of the node link diagram within the cluster glyph. Other suggestions included the extensions of labeling individuals, groups, and timestamps. The main component of our visual design is the visual abstraction of the spatiotemporal network links and group structures. The effectiveness of these abstraction methods, however, depends heavily on the underlying network data, which is usually generated by the usage of a similarity metric, for example the Euclidean distance between attributes of a mover. Furthermore, we currently use the STDBScan algorithm for the spatiotemporal clustering. This clustering algorithm is however not able to capture clusters with different spatial distributions. We implemented the ST-optics algorithm to overcome this shortcoming. Another challenge is the placement of the cluster glyph, which is currently the centroid of the group. This can again create overlaps between groups and single movers. Overall, the results of our iterative design process is a glyph that enables us to display. Another challenge is the placement of the cluster glyph, which is currently the centroid of the group. This can again create overlaps between groups and single movers. Overall, the results of our iterative design process is a glyph that enables us to display a visual summary of dense spatiotemporal network data, which are typically hard to visualize. The designed glyphs are suitable to visualize any kind of spatiotemporal network data, even though the application was clearly motivated by collective animal behavior. The prototype and the code for motion glyphs are available online. Thank you for your attention.
For animals, and we have several positive comments in the chat, and we also have a few questions. So maybe let's start with the first question. It's about a hybrid approach. So the question is, could you imagine that you combine a graph approach with something else, where you, for instance, use matrix design for very dense areas to show those. Have you thought along these lines?
So there are like a few drawbacks of showing like a matrix visualization in general, but I think having an additional view in which you display also like the drawbacks are like that you don't show like the spatial positions from which like these network links are like influenced. But on the other side, like having like an additional view where you have like some matrix visualization over time could really help to like find also interesting patterns like in the overall temporal dimension. Yeah.
Okay, thank you. We have another question about partially drawn links. So the question is, have you also considered or tested partially drawn links instead of the ring chart to indicate edge information? Maybe 10% of the link at both start and end. Have you considered this?
Sorry, I think I stuck shortly. But yeah, we also considered that. Well, like also drawing partial links, something like instead of having like this donut chart at the end, or also like a sunburst diagram where you also indicate or have like these partial links. But it was like really also challenging to see the differences on these small scales, which was like hardly or like also produced like some visual clutter.
Okay. I was a bit wondering about scalability and the clustering. So you perform a clustering, if I understand correctly, based on some clustering algorithm, but this gives you a feeling of what a group is. But I was thinking the animals should also behave if they are part of a group, or perceive if they are part of a group or not, maybe, right? So this clustering introduces some group notion which might not be experienced by the animals of the actual flock, or whatever you want to call it. Have you thought a little bit about this, if this introduces something in the visualization which might not be there?
Yeah, so the general thing that you include like these, or like generally generate these notions of groups by some kind of metric, which is like in that case, we used like the Euclidean distance between the different attributes of a animal. So like for fish, it was like speed, acceleration, direction, and the spatial distance. So depending on that, for sure, we will have like different group notions. And in our tool, domain experts can also define those notions which they think is like a group. So in general, they consider animals that are close to each other and have like similar behavior, which is like they have like the similar swim in a similar direction, have like a similar speed. They consider this like to be like a social group. But for sure, different notions of these definitions of these similarities also will result in different group structures. And we also support that in our tool.
And with respect to scalability, when you show this group graph inside the glyph, there's not too much space. What are your observations there in terms of sizes?
Yeah, so I would say it's difficult to spot like smaller changes in these cluster glyphs, as you will also have again edge crossing and node overlaps. And we were also thinking about in general to also apply a nested glyph design, so that we would have like also glyphs in the cluster glyph, and we also tried that out and we described that in our paper. But this was again a little bit more confusing, as people thought that the inner glyphs would also relate to outer glyphs. So we also tried to scale up the cluster glyph, but the complexity again was like quite huge then, increased.
Okay, yeah, thank you very much. Let me see if we have another question. Yeah, so someone comments also, defining animal group membership is a difficult challenge. This is too okay, this is more like a comment. That this is another challenge. We have another question here. How do you handle granularity? granularities in your approach?
So like for the STDB scan, the STDB scan algorithm that we used was not able to capture different spatial distributions, and we got that also as a feedback from a reviewer. And after that, we implemented the ST-optics algorithm to capture that. And I think if you go to the GitHub repository, you can also find that implementation there. So we extended the work so that it also includes or can capture different spatial temporal granularities.
Okay, then many thanks again for a nice presentation and giving great answers to the questions. I would then suggest we move on to the next talk in this session. And this talk is about, again, a very different topic. It's about cultural heritage data. And the paper is entitled Reading Traces, Scalable Exploration in Elastic Visualizations of Cultural Heritage Data. And the talk will be presented by Mark-Jan Bludau, and he's a research associate at the University of Applied Science in Potsdam, where he focuses on visualization in the area of cultural heritage. So let's start the video and enjoy his talk.
Hi, I'm Mark-Jan Bludau, and this is a presentation about our paper, Reading Traces, Scalable Exploration in Elastic Visualizations of Cultural Heritage Data. And today I'm also representing the team behind the paper, our team from the UC Lab of the University of Applied Sciences Potsdam, Victoria Brüggemann and Marian Dirk, and of course also Anna Busch from the Theodor Fontana Archive and Potsdam University. And this talk is mainly about a design study that we did. You can see first impressions of it in the background, where we visualized reading traces such as comments, corrections or markings inside the books of the author's library of the German realist author Theodor Fontana. And by presenting this design study, we also want to present an approach that we developed to data exploration that utilizes elastic visualizations designed to support and move between varying degrees of detail and abstraction. Here, we were especially interested in the potential of carefully designed transitions and consistent representations across scales. We first want to look at the title again. Scalable Exploration in Elastic Visualizations of Cultural Heritage Data. What do we mean by that? First, with the term scalable, we don't refer to scalability in the sense of algorithmic processing of large data quantities, but rather to the comprehensible scaling of visual representations between different levels of granularity, complexity, and abstraction in an information visualization. And with elastic visualizations, we refer to coherent representations that integrate interactivity and visual encodings with the aim of achieving coherence and context across multiple perspectives. And finally, we were especially interested in exploring the notions of elasticity and scalability with a focus on cultural heritage data, like cultural collections from museums or archives, because here to us, the richness of the data makes the interplay between close views on the level of individual items and distant views from broader patterns especially useful. Even though there won't be time to get into details, just to give you a more concise idea about our considerations and related concepts that formed our approach, we want to show you some related research. First of all, our approach relates to research in the digital humanities and the ongoing debate about the appropriateness and usefulness of quantitative techniques such as distant reading compared to qualitative approaches. Additionally, regarding exploration of cultural heritage data, our design study is in line with an increasing research interest with the goal to expose the richness of such underlying data through generous interfaces. In service of open-ended exploratory experiences, our research is also related to the concept of flow and building on this, fluid interactions. Furthermore, it relates to techniques to move between varying levels of details and complexities, such as focus and context techniques or semantic zoom. And finally, it relates to the growing research interest on the potential of using transitions in data visualizations. And while semantic zoom commonly supports a form of vertical scaling, it is usually limited to zoom and neglects the possibility for differing granularity levels of data on the same horizontal plane. Focus context techniques, on the other hand, are oftentimes used to deal with varying complexities on a horizontal level, but fail to integrate vertical zoom operations. Our goal was to achieve continuity with multiple arrangements and levels of abstractions, while simultaneously considering information structure and representation changes. Therefore, with our design study, we propose to imagine a visualization as an elastic space that can be adjusted through stretching, contracting, or folding on multiple levels of granularities and abstractions, while preserving coherence and context between representation states through carefully designed transitions that ideally facilitate the comprehension of the abstraction processes. So, contrary to a practice of first focusing on the encoding and adding interaction and transitions between representations as an afterthought, to achieve this form of elastic visualizations, we therefore argue that it is necessary to think about encoding, interaction, and transitions in unison from the start. To further explore the notion of scalability and elasticity, we did a design study about reading tracers in Theodor Fontana's personal authors library, a collaboration between the UC-Lab and the Theodor Fontana archive. The collection Fontana's authors library is a collection of around 155 books, not necessarily written by Fontana, but books that were once in Fontana's possession. Fontana held these books and he worked with them, and this can be seen in numerous reading traces in the books, such as comments, ratings, text corrections, markings, institutional stamps, fingerprints, or glued-in newspaper articles. Furthermore, the case study and our approach of elastic visualizations built on each other, because for the researchers of the Fontana archive it was a priority as well to facilitate both quantitative and qualitative encounters, stretching from the level of individual reading traces to the level of broader patterns in the whole collection. In a rapid prototyping process, we iteratively generated small prototypes and conceptual sketches to familiarize ourselves with the collection, to identify first interesting patterns, and to stimulate discussions with our partners. Finally, the result of the whole process is this prototype, which is divided into two modes, each one consisting of multiple granularity levels to help explore the data from different perspectives. While the first mode, on the left side, arranges and visualizes the distribution of reading traces along the linear reading order of the books, the second mode displays books and authors based on similarity measures. In the first mode, each book is represented by a vertical bar, ordered by authors, and each page of the respective book is represented by a segment, ordered from first to last page of the book, from top to bottom. Pages without reading traces are displayed in white, and pages containing reading traces are colored according to their category. For example, marginalia in red tones and markings in blue tones. And if I scroll up now, or use the navigation bar to do that, the visualization transitions to a new view where the average total distribution of reading traces within all books of individual authors are shown. Scrolling down, on the other hand, allows a detailed zoom into the books with view on individual pages and reading traces. If I now click on a book here at the book level, additional details can be unfolded, and a preview of the digitized pages of the selected book can be viewed. And using these filters at the top of the page, it's possible to focus on individual categories of reading traces, while unfolding additional subcategories. If I select a book at the page level, or scroll from a selection from the book level to the page level, I get access to individual pages and reading traces, including the transcribed marginal notes and the presumed identification of their author. And additionally, on click I can view a detailed view page. Now, if I go to the buttons in the top left corner, the mode of the visualization can be changed to a dark mode, now arranging books and authors based on similarity measures, using a form of multidimensional scaling of quantitative reading trace occurrences. Here it's possible to navigate between two granularity levels through scrolling. A book level, arranging all books based on similarity of reading trace occurrences, and an author level, arranging the authors in the collection by similarity between average numbers of reading trace occurrences in their books. Because of the similarity-based arrangement, books or authors with similar reading trace occurrences are displayed closer to each other. This leads to the result that books or authors with more special reading trace occurrences tend to be positioned more towards the outer edges. At the book level, a click on a book highlights all books of the same author, marks the average value of their books through a network graph, and opens a side view with additional detailed information for the selected book. At the author level, a click on an author opens another sidebar, which gives an overview of the reading traces and the book covers of all books of the selected author. Moving between the two modes, all selections and filters will be adapted to the new view, enabling fluent motions between both modes and the granularity levels. In addition to comments and insights from our literary collaborators, we were interested to get fresh feedback on the potential of our approach, so we conducted an open-ended think aloud study. One interesting observation was that many participants called both directions of the granularity changes zooming in, even though from the description it was clear that they understood the difference. The use of scrolling to control transitions has triggered ambivalent reactions among the participants. While some of them seem to benefit of scrolling for the sense-making of the visual changes and data operations, which could be seen by slowly scrolling back and forth, others were confused by incomplete in-between states or the interaction through scrolling itself. Nevertheless, we noticed that the easy access to multiple levels oftentimes seemed to promote exploratory behavior. Half of the participants highlighted the smooth movement between the different connected levels as helpful and noteworthy about the visualization. To wrap up this presentation, we think that with our paper we make two main contributions. First, we introduce scalable exploration as a design principle for the creation of current information visualizations. And second, we present the results from an interdisciplinary design study with literary scholars, in which we devised elastic visualizations of a reference library and did a first qualitative evaluation. And even though our evaluation in fact paints a kind of ambivalent picture, at least regarding the use of scrolling for controlled transitions, we see promising indicators for the facilitation of exploration and engagement in the use of scalable interfaces. And of course, you can find a lot more details in the paper, and furthermore, feel free to check out our prototype online. And that's it. And we are happy to answer questions or to receive feedback. Thank you.
Mark Jan for a wonderful presentation. People are amazed by your user interface. You got a lot of positive comments. You also got a few questions. So one, I think you partially reported it in the user study, but not entirely. So I will ask the question anyway. So the question is, do users get confused with the different zoom options, or does it feel natural? So you were commenting on the scrolling there. I guess this is related. Can you elaborate a bit more on this, please?
Well, I guess the scrolling for some of the users, of course, is a bit difficult, because it's some kind of another way to navigate on such a website. So it was sometimes a bit confusing, especially regarding the in-between states. So some of the users got somehow lost in the in-between states. So we now see that there should be some kind of automatic threshold to bring the users back to the main stages. So yes, it's, for some people it was a bit of a problem sometimes, but on the other hand, it was kind of helpful for the exploration because they move back and forth for many things. So if they found something in one level, they could easily go to another level and keep the focus on something.
Okay, yeah, thank you. There's another question here, if there's different version for desktop and mobile, and if that's something where you have noticed differences in preference for domain experts, if they preferred one over the other.
So the prototype was planned to be for just a desktop application. So the touch version was more or less of an afterthought because it is the Fontana year right now, and there was an exhibition. So there was the idea that we could present that in the exhibition, but actually it wasn't quite optimized for that. So we had to change a lot of things, and I would say, at least with the version right now, it's not like an ideal situation to use the prototype on a touch table. But I think in general, our domain partners also like the touch table version because they could present it in their own exhibitions or in their own places.
Maybe this is a good opportunity to ask about the technical realization. You have said very little about this, if at all. Can you discuss this a bit more? What's the backend and how did you realize this?
So actually, we are only using CSV files where the data is collected, and for the design and the transitions, I used D3.js mainly and a mix of Canvas and SVG. So yeah, in the beginning was a bit difficult to get. And it still is for some older computers to get the transition smooth because there are a lot of elements moving, but yeah, it's mainly D3 based.
Yeah, okay. And then we have another question. Since the 2D positioning seems to come from many parameters, can it be used to answer questions like, which books were annotated by this person?
So right now it's mostly based on it's the collection by Theodor Fontane. So most annotations are actually by Theodor Fontane himself, and only a few are by his family or the archive. For example, stamps by the archive also are inside. So you can't really see that right now because we didn't focus on that. Yeah, that's.
And maybe then I have another question related to this. How can you generalize this? I mean, people really like the interface, and I could imagine this works in very different domains as well, and it would be great to have some easy-to-use library set up or something along that line. Have you thought toward that? And if yes, what would be the process?
So yeah, while it's mainly we did it mainly for this specific collection, but we also went, for example, to a congress only for authors' libraries, which is like a specific field where all people are only discussing about marginalia in such libraries, and we think that it could also be used for other libraries. But of course, the scalability is. We would have to change things because of scalability limits, because the library we are using is only around 155 books, but there are other libraries like with 2,000 books or something like that, so we would have to modify it in some way.
Okay, good. Thank you very much for nicely answering the questions and giving a great presentation.
Thank you as well.
We would then move on to the next and last talk of this session. And this talk is given by Shivam Agrawal, and it's about a game. It's about the bomb playing games, which most of you probably know, and some of you have probably played. So it's called Bomballistics, Visualization of Competition and Collaboration Strategies of Players in Bomb Playing Game. And Shivan is a fourth year's PhD student at the University of Duisburg. And he says he works on a variety of topics on visualization, And today he will inform us how to apply this to analysis of strategies in these types of games. So let's enjoy his talk, and then we can have some questions to him afterwards.
Hi there, my name is Shivam. Today I am going to talk about a new approach called Bombalytics. Cool name, right?
My name is Shivam.
Competition and collaboration in dynamic environments are a result of complex interactions. Analyzing these interactions is both important and challenging. Analysis of interactions and event sequences reveals insights. In return, these insights help in improving our understanding of how entities behave in these environments. To quote Bateman and Gottman, defining characteristics of interaction is that it unfolds in time. To begin our research, we needed interaction data from some environment where entities compete and collaborate. We showcase our approach and tailor it for a multi-agent game environment called Bomberman. In each battle, there are 4 players located at the corners. 2 teams compete to win the game. Teammates are located diagonally opposite to each other at the start. The battle arena is a grid of 11 rows and 11 columns. There are 3 types of tiles in the grid. First is the navigable space. Second is an unbreakable rigid wall. Lastly, the third type of tile is a wooden wall that can be broken by a bomb. The action space of agents is simple. In one time step, an agent can either do nothing, move in one of the 4 directions, or drop a bomb. A bomb explodes in exactly 10 time steps. The flames of the bomb persist for another 3 time steps. By default, the blast radius of a bomb is 1. Additionally, each agent can lay only one bomb at a time and needs to wait for the bomb to explode before dropping another one. An agent dies if it comes in contact with the flames. The objective of the game is to eliminate enemies. A battle ends when all players of a team die or if the battle exceeds 800 steps, resulting in a tie. To make battles interesting, 3 types of power-ups are hidden beneath the wooden walls. Extra bomb power increases the count of bombs that can be laid simultaneously by 1. Similarly, increased range power-up expands the blast radius by 1 tile. And finally, the can kick power-up enables an agent to kick the bombs. Let's watch a battle playback between 2 teams from the competition held in 2018. The Bomberman game has an active research community of artificial intelligence developers who train their team of agents for annual competitions. The Docker containers of all agents participating in the competitions are available online. Hence, the Bomberman environment serves as a test bed for the researchers as they can evaluate their training approach by competing with other teams. In doing so, the researchers have trained agents that seem to exhibit complex behaviors. Currently, the performance of 2 teams is judged by counting their number of wins and defeats in a set of games, which is approximately 50 in annual competitions. We chose this game environment because in each battle, agent needs to interact with the environment while competing and collaborating with other agents. So far, battle playbacks have been used by the researchers to analyze the gameplay behavior of teams. Although playback helps in step-by-step analysis of a game, they do not provide an overview of the events in a game. The playbacks also increase the cognitive load that makes it challenging to infer any strategies demonstrated by the agents. To address the challenge, we started with 3 design goals. The first goal stated that the solution should provide an overview of events that occurred in a game. The overview should help in deriving inferences, such as whether agents collect more power-ups at the beginning of a game or not. Second, it should be easy to find local patterns and repetitions of agent interactions. This would allow us to answer certain questions. For example, did agents learn to kick bombs? If yes, then who dropped the bomb? The agent itself its teammate, or its opponents. Finally, the third design goal focused on providing an overview of multiple battles played between two teams. It would help in evaluating the performance of two teams over several games. We implemented our approach as a web-based prototype. The interface has four main components. The summary component at the top abstracts all the games played between two teams. A timeline visualization at the center shows details of a selected game. Histograms at the bottom show the temporal distribution of a selected game metric. And finally, playback at the top right replays the selected game step by step. Let's dive into the timeline component. We use colors to encode agents' actions and events during the game. For example, movement is shown in orange and kicking a bomb in pink. The horizontal axis denotes the progression of a game from left to right. Meanwhile, the vertical axis shows agents and power-ups in individual rows. Since power-ups are common resources, we place them in the middle, while agents are positioned at the top and bottom of the power-up rows. Bombs are shown separately for each agent in their respective rows. We represent a bomb by a circular head, indicating the drop, followed by a dashed line that denotes ticking of the bomb, and a rectangular tail at the end showing blast duration. The interactions are shown by vertical lines, linking corresponding entities. For example, the power-up action shown by the green circle is linked to the type of power. So we draw a vertical line between the corresponding rows. Similarly, bomb kick and deaths are linked to a bomb via vertical lines. To explain it with an example, we can say that here agent 3 collected 2 increased range power-ups, followed by a can kick power-up. Later, the agent kicked 2 bombs laid by itself and goes on collecting more instances of can kick power-ups. We can already infer a few interesting strategies of agents from the timeline visualization. Here we can see that Team A, the top 2 rows, did not collect any instance of extra bomb power-up. The agents of Team A repeatedly drop bombs and move. They also kicked their own bombs a few times. In contrast, agents in Team B collected many power-ups and laid fewer bombs. There was one instance where an agent of Team B kicked a bomb dropped by its opponent. On an overview, we can say that both teams compete to power up at the beginning of the game. We conducted an expert study with 20 participants and asked users to explore the implemented tool. The experts were able to find many competition and collaboration strategies exhibited by agents. For instance, one of the experts mentioned that the 2 agents of Team A seemed to collaborate by behaving differently. One of them plays defensive and tries to survive the game, while the other takes more risks and kills enemies. Okay, we have built an approach that was targeted at developers of agents for the Bomberman environment. So what? While the implementation is tailored for one environment, we envision the approach to be applicable for several games. The approach can be applied and extended to analyze competition and collaboration behaviors in strategy-based games. For example, League of Legends and StarCraft. From a more general perspective, we can also use parts of the approach in analyzing interactions from real or virtual environments. For example, it can be used in the analysis of multi-user VR sessions from games and remote assistance. The experts also suggested to include the spatial aspect of interactions in the timeline visualization, which we plan to do in the future. We hope that it would make it easier to infer more complex competition and collaboration strategies from the visualization itself. Don't forget to check out the demo of the tool and the paper for more details. Thank you for your attention.
think we're still okay. Thank you very much for a great presentation. A very interesting and fun project, I think. I was thinking you talked a bit about generalization to other games that you were mentioning these computer games, but we also heard a lot about AI solving games like Go, which was huge in the news. And there it's a little bit more difficult maybe because you don't have this specific actions which you were introducing in the beginning of your talk. It's for me at least a little bit hard to imagine how this could be transferred. Have you thought about this? Do you have any ideas how to do a transfer in such an area based on the techniques you do?
Yes, thank you for the question. I'm glad to be here. That's a great question. Actually, I was also surprised in the beginning by seeing the variety of games, and that's where collaboration with Gunter, who is actually the game analytics expert, I got to know that okay, these different kinds of games demand different visualizations to analyze them. So, as you said it rightly, that game-based approaches won't work in action-based games. So, yeah, the visualizations will not be. A lot of them won't be transferable to those kinds of games, but parts of them can be definitely used.
Okay, yeah. Do we have further questions? Let me check in the YouTube. Okay, there's no questions for now. Let me then ask. So you've tested this with users. I didn't hear you saying that you plan to release it, which is a common thing in the learning community. Are there any plans for that? And will people of this Bomberman then be able to use this while training to compare their own models, maybe, and things like this?
So thanks for the question. Actually, I forgot to include that in the video, but the implementation is already online and the link is in the paper itself. I forgot to include the link in the video. The code and the responses, everything, it's there on the OSF, so feel free to check it out. And the code can also be extended. So I mentioned the expert study, and that we conducted with 8 of the Bomberman experts who make agents. So they found it useful and they plan to use it in future competitions as well. So this is already online and it is being used and has been received well by the community.
Okay, great. Yeah. So a couple of more questions popped up, or one actually. The question is, so did the graphics and the design get the analysis to ask new and different questions? So did they get further insights of things they haven't thought about beforehand?
I can verify that yes, from the expert study and from the informal feedbacks we have received, they found few glitches in their own AI agents which they wanted to improve further. So yes, they found unusual behaviors in their agent and also strong strategies in their opponents. So these are the few things which we have received in the feedback.
Okay. Great. Thank you very much again for a wonderful presentation and a really cool tool. So we have seen now all 4 talks and we had the Q&As. And since we had some sound problems at the beginning after Theo's talk, I would like to ask if it's possible that Theo comes up again and we do a Q&A regarding talk number 1.
Yeah, I'm here.
Ah, you are here? Okay, I can't see you. I'm sorry.
Sorry, turn it on. Is it okay?
Sorry, what?
I turned my everything on.
Picture only. And you are not in the YouTube channel. I just checked. Yeah, never mind. I hope people can hear you on the YouTube channel. So yeah.
Oh
thanks.
yeah.
Okay, so apparently they can hear you, and I can see you now also. So we have a couple of questions from the YouTube chat, which I thought would be interesting to ask you. And the first one is, I guess reordering the rows based on different metrics, for instance, similarity, could reveal patterns in memory activations. Any thoughts on that?
Well, yes. One main issue of GLVs is its exploration, and one way to do that is to guide users. And in the previous version of GLVs, we tried to use metrics so the timelines at the bottom of the memory to filter the memory and on rule-based systems. But the main issue with that is that you have to make the users trust these rules to understand what's going on in the memory. So we had, for example, filters based on how much health the agent has or stuff like that. But it's hard to analyze which kind of patterns you want to go with that because you have to trust the system itself. So in the long run, we just remove this issue.
Okay, yeah, thanks. And another question is regarding your manual comparison, where you actually moved over these patterns. And the question is, the manual comparison seems to be time-consuming and not prone to errors or overlooking. Did you consider automatic pattern matching to help users finding the matches? If yes, which advantages or disadvantages do you see with such an automatic approach?
Oh yeah, yes. As I mentioned, we try to implement such automatic patterns detection. This is in particular useful because when you try to look at the memory, you may want to observe patterns that are not related to the image itself, so the observation of the agent. And therefore, the application of automatic pattern detection is very useful in this case. But sadly, as I mentioned earlier, the main issue is that when we presented such tools to experts, they had trust issues on what's going on and what they thought. So we did not use them. But this is an interesting future work, and we are currently working on that.
And then maybe one final question. I would be interested to know about generalization. You have talked about different scenarios, but to me, the scenarios seem to be very similar, if I might say. So it was all navigation in some game-like environment to collect something or see something. But I mean, deep reinforcement learning, of course, has many, many more applications. Can you comment a little bit about what could be used in very different scenarios and what could not be used of what you have presented?
In most cases, GLVs can be used as long as your deep reinforcement learning model has a memory, the recurrent part. So it can be used, but to have GLVs at its full capacities, you have to apply it to navigation tasks. We are currently working on using GLVs outside the simulation, so with a robot moving in real life situation. And in this case, since it's still navigation, a problem where the agent needs to move in the environment, every part of GLVs is applicable. The only issue with real life is ground truth, because in GLVs we exploit for the timelines, for example, information coming straight from the simulator, for example, items in the field of view of the agent, which is not available in real life situations, this kind of information. So the timelines needs to be a bit adapted to be able to use that in different simulation and environments.
Okay, great. Thank you very much. With that, we approach the end of our session. I would like to thank all four speakers again for giving great presentations and being very informative in the Q&A sessions. And I would like to also, of course, ask the technicians who made this all possible. And of course, you, thanks a lot for listening. And with that, I would like to say goodbye. See you soon.